And from now on, we'll restrict our attention to the homogeneous case. So we set this alpha equals 0. So you may remind yourself that a property for the determinant of an orthogonal matrix is the following. It has to be plus or minus 1. And you could show this result by taking the determinant of this equation here. Just as we did in the case with these rotations in 3D, in the previous chapter, we may classify different Lorentz transformations according to whether the sign of the determinant is plus or minus. So in the case where the determinant is plus 1, we call it a proper Lorentz transformation. And minus 1 is an improper Lorentz transformation. If you remember, we argued that in the case of three-dimensional rotation, we could obtain this minus sign only for unphysical rotations, like impossible rotations. We used an example, I think something like this. Where I transformed this coordinate system to this one. And I challenged you to try to find a way you could rotate this system to this. And I think we agreed that it was impossible. Because this corresponds to an inversion of the coordinate axis. So there's no way I can obtain this system simply by rotating this system. And the transformation corresponding to going from here to here will have a determinant equal to minus 1. And one might then speculate if this is also the case for a Lorentz transformation. If we invert the space axis, is that allowed? Do we get plus or minus 1? What do you think? So the question is, if we perform an inversion of the space axis, do we get a proper or improper Lorentz transformation? So we're doing this. So what is the corresponding Lorentz matrix? Does it have any off-diagonal entries? No. Okay. We should have something here. So something like this. So the question is, what is on the diagonal?
It's -1, -1, -1, and then 1.
And the determinant of this matrix is -1. Exactly. So inversion of the space axis gives us an improper Lorentz transformation. However, we now have a fourth dimension to play around with, which can actually rescue us from this situation. Because we see that if we invert the time axis as well, the determinant becomes 1. So this additional time dimension adds an additional aspect regarding the classification of different Lorentz transformations with regard to their determinant. Now there's another useful property which we can derive as a general result. And that is that the L44 element, this element, of any Lorentz matrix, if you square it, it has to be larger than or equal to 1. This can then actually constitute a useful check in your calculations, because say you are asked in your exam to find, for instance, a Lorentz transformation matrix for some particular transfer between two coordinate systems. And you find some matrix and you're wondering, is this the correct result? Well, one check at least is to see if this is the case. If it's not, then it's wrong for sure, at least part of the matrix. So let's prove this. So we start out with this relation for orthogonal matrices. And written in terms of these components with an implicit summation over alpha due to the repeated indices, we write it like this. So the transpose is simply obtained by shifting the two indices. So consider now the case where mu and nu are equal to 4, because we're interested in this L44. So we get this. If mu and nu are equal, this is 1, and we get L4 alpha squared, and a sum over alpha. Now, keep in mind the Greek indices represent these 4-dimensional vectors. So if it's a summation over a Greek index, it means that we sum over both space and time coordinates. So I can write this sum in the following way, where I now extract the time part, the L44 element, and then write the remaining sum with a Roman index to indicate that we're now summing only over the 3 first coordinates. And keep in mind that for this particular metric that we've chosen, and I'll get back to the metric in about 10 minutes, the 4 vector we've chosen, the convention for this last coordinate is that it's imaginary. Now, L4I corresponds to the coupling between the time coordinate and the space coordinates. So you can see this from this transformation equation, that the final element in x prime, which is the time coordinate, which is imaginary due to this convention here, is in general a superposition of contributions from the spatial and the time terms from this vector. So the first 3 elements in the last row of L correspond to the coupling between time and space. And since the time coordinate here is imaginary, well then these couplings also have to be imaginary, since they couple an imaginary time with a real space coordinate. So since these L4I, or J here, I can just use I. Since these L4I elements have to be imaginary, their square has to be negative, or 0. So we know that this sum is either negative or 0. And as a result, L4 squared has to be larger than or equal to 1, simply by moving this term over here. Now, since the L4 squared element has to be larger than or equal to 1, we have 2 possibilities for L4 itself, because this equation can be satisfied both for a positive and negative L4. Oh, sorry, -1. So the point of this is that in addition to the classification of the Lorentz matrix as proper or improper depending on the sign of its determinant, we have one more classification depending on the sign of L4. We either have time inversion or not. Or more accurately, we have a non-orthochrone or orthochrone transformation. So that's a bit about the mathematical properties of a Lorentz matrix, and in particular in relation to these 3-dimensional rotations that we considered previously. Now, as I've been saying for quite a few times now, I will say a few words about the metric that we've used. And whereas this is not a very big deal in this course, the metric you will learn a lot more about if you proceed with more advanced theoretical physics courses, such as field theory, for instance. And to consider the metric, we introduce a couple of concepts to begin with. So what we'll say is that these four vectors live in a so-called Riemann space. The Riemann space has coordinates x mu, which may be either real or complex. So the Minkowski space is a special case of this. And the square of the length of a path element in this space is defined like this, where g mu nu is the metric tensor. And this metric tensor serves a special purpose because it's used to distinguish between covariant and contravariant vectors. And the way we do this in terms of notation is to use either a lowered or raised index, a sub or a superscript. So the way that the metric tensor relates these is as follows. So a covariant vector with a lower index is given by this sum here. We also have a repeated index nu of g mu nu x nu, where x nu here is a contravariant vector. So one way to think of this is that the metric tensor lowers the index. So the contravariant vector has a raised index here. This metric tensor lowers it so that it becomes a covariant vector. And completely in the same way, you can obtain a contravariant vector with a raised index by raising the index of a covariant vector here by using the metric tensor. And you might be relieved to know that the metric tensor, for the metric tensor itself, you can use either subscripts or superscripts, so it doesn't matter. but it's conventional to write these indices as subscripts when you want to lower the index of a contravariant vector to a covariant vector, just as a bookkeeping device. So the main point here is just that the metric tensor relates covariant and contravariant vectors by raising or lowering the indices. So using our definition here for this infinitesimal path element in the Riemann space, we have this, where I've now just rewrote the metric tensor according to this. I just raised the indices here. So we see here now that this part summed with this part becomes a contravariant vector. So I combine these two elements here into this. So if this quantity ds squared is an invariant in all inertial systems, for instance, well, this product of the covariant and contravariant vector here is also an invariant. Now, when we first started on this chapter, we considered the two postulates of the special theory of relativity. And one of them was that the speed of light should be a constant in all inertial systems. And we demonstrated this in particular by showing that this quantity would have an invariant form in any inertial systems. So we basically took this, which was the equation of motion for a wavefront of light in our system S. We Lorentz transformed this to a prime system moving with a relative velocity v, and saw that it had exactly the same form, so that the speed of light would be the same. So this is our invariant. This has the same value in both inertial systems and in all inertial systems. So we have operated with the fourth coordinate being ICT so far. So we have the following 4-vector. And now I have a little task for you. With this choice of our 4-vector, what is the metric that we have used? In other words, find the matrix G. So take a minute to do that. Okay. Any suggestions for G?
All ones on the diagonal except the last one, which is -1.
Okay, let's try. So you suggest that G is like this. Okay. So then, if you use this equation here, we should get this. Do you agree? Should be plus. Because the I squared here gives a minus. So if we do like this, we get the correct form. So actually, the metric tensor has a very simple form for this choice. It's just the identity matrix. And if it's the identity matrix, well, that has an additional nice consequence, or at least convenient consequence. And that is that the covariant, the distinction between covariant and contravariant vectors vanishes. If this is just identity matrix, then x mu with a lower index is equal to x mu with an upper index. So for our choice, for Minkowski space, where you have this fourth coordinate, ICT, the lower and upper indices don't matter, we can write the path elements like this. So in order to say something about which metric we've used, we can say that we have used the identity matrix. That's fine. But there are, as we shall see, different possible conventions for which metric we want to use. And in that case, this matrix can become more complicated. So a usual way to classify the metric or the matrix G that we've used is to classify it by its trace. Are you familiar with the trace of a matrix?
Just the sum of the diagonal.
Yeah. So it's the sum of the diagonal elements. So for this particular metric we have that the trace is equal to 4. All right, but as I said, this is just one possible choice. There are other ways we can obtain this invariant path element in Riemann space. For instance, So I've here labeled the coordinates from 0 to 3 instead of 1 to 4. But we still have 4 coordinates. All right, so using this representation here, which metric do we need to get an invariant path element? So take a minute to think. So what we want is to obtain this path element. This path element is defined in general like this. So the question is, with this choice for our 4 vector, which is different from this choice, what kind of metric do we need? Any ideas?
-1 from the first element. The rest of the diagonal is just 1.
Like this? Okay, let's check. So we get ds squared is g00. 0. We get something like this. So this is minus c which is fine. So for this choice of the 4 vector, we need this metric to make the path element invariant. Is that the only metric that will do the trick? Actually, there's one more choice. (1, minus 1). So just by multiplying the metric tensor with the minus, an overall minus sign, well, then would you just get c squared t squared minus this norm of the space of the spatial position vector. But ds squared would still be an invariant. It's just an overall minus sign. So both of these choices for the metric tensor will give us an invariant path element in Riemann space. So we see then that the classification of these two metrics are different. This one has trace 2. Sorry. Overall minus sign. Should be like that. And the trace here is minus 2. So for a given 4 vector, there are at least 2 possible choices for the metric. So the point of this intermission with the metric was just to raise your awareness of these issues. So in this course, we'll use this identity metric tensor for the Minkowski space so that you don't have to worry about covariant or contravariant vectors. Okay. These arguments sort of originate from this necessity to have a constant speed of light. But the other postulate of the special theory of relativity was that the laws of physics should be the same in all inertial systems. So let's consider that. And perhaps somewhat unfortunately, the terminology in this field is such that Lorentz invariant, another word that is used for it, is also covariant. But this covariant has nothing to do with the covariant and contravariant vectors that we introduced here. So that's a bit unfortunate. So we may think of this as Lorentz invariance, if you will. And what we want to say something about is now the second postulate, that the laws of physics should be Lorentz invariant, meaning that if we go from one inertial system to another, they should be the same, which means that they should be invariant under a Lorentz transformation. And then just know that this is also sometimes called covariance of these laws. So we want to check if all the laws of physics have the same form in all inertial systems. In other words, they should be form invariant under a Lorentz transformation. So how should we check this? Well, the laws of physics can be described by equations. It can be scalar equations or vectorial equations or matrix equations. So scalars and vectors are just special cases of matrices. A scalar is a one-by-one matrix. So what we're demanding here what we're demanding is that if you have the following equation describing some law of physics, where you have, in general, then a matrix equation, which may be a scalar equation just in the special case of a one-by-one matrix, you have C equals D. Then if you Lorentz transform both sides of the equation, so you get C prime equals D prime, they should have the same form. So by Lorentz transforming both sides, the equality sign should still hold. And this is known as covariance of the equations. And we'll actually have a quite detailed look at the theory of electromagnetism to see if this holds. Before doing so, we should introduce a couple of preliminaries. Now, a particle moving through Minkowski space has a trajectory which is known as a world line. So think of the world line as some trajectory through this four-dimensional Minkowski space. Now, a small change in the coordinates of the particle is represented by dx mu. X mu is the position vector, if you will, in Minkowski space. So we can represent an infinitesimal path element like this. And we know that this is an Lorentz invariant. It's the same in all inertial systems, which we have proved. So since it's a Lorentz invariant, we may define a constant quantity here, namely the Eigen Time, which is known as tau. We define it in the following way. And if you're wondering why we define it in this way and why it's called Eigen Time, I encourage you to come to the next lecture. Thanks for today.